Okay, everybody, I think we're going to get started again. So this morning's session, I think we had some great presentations. We learned a lot about how paying attention to the basics and the simple fundamentals can really make a big impact. And it's not exclusive to only large data centers. And it's not exclusive to only data centers that are that are not designed for ultimate availability. I think Mark did a great job explaining how the improvements, even with a traditional banking type of a data center infrastructure, can yield great benefits and really impact the bottom line very substantially. And I think that one of the messages that was clear is, from Dean's presentation with eBay, followed up by our panel discussion, is that there's no one right solution. And we firmly believe that, and we've been implementing a variety of different free cooling solutions throughout Europe. So now I'd like to take you on a tour of Northern Europe and some of the free cooling solutions that Google has implemented in our data centers. By free cooling, I mean that all of these designs are 100% chillerless, so no compressor-based, refrigerant-based chilling. Okay, I think one of the things that I love about my job is that we're given the opportunity to think outside the box and to look for local opportunities based on climate and geography and take advantage of those. So the presentation is going to take us on a tour through Belgium, Ireland, and Finland. I've spoken extensively about our data center in Belgium at our previous conference 2 years ago, and subsequently since then. We'll go through and talk a little bit more about that design, which is a 100% waterside economized design, no chillers. In Ireland, this is a colo data center that we performed a retrofit on, and that is an airside economized solution. I'll talk a little bit more about that. And in Finland, our latest production data center, which is a direct seawater cooled, direct heat exchange with seawater. Once again, no chillers, no compressor-based cooling. So first, on to Belgium. Our site in the Walloon region of Belgium is Google's first completely chillerless design. We employ a full waterside economized solution. That means that there are no chillers and we only use cooling towers for heat rejection. And another unique feature is that it's 100% gray water. So there's a local industrial canal nearby, and we built our own water treatment plant on site to treat that water before we use it. We've achieved really great results, PUE-wise and efficiency-wise with this site so far. It came online in the second half of 2008, and our last quarter in Q1 this year, our quarterly average PUE for this site was 1.09, and the trailing 12-month average is 1.11. So this is really outstanding efficiency from this design. This is a picture of the site, and you can see that it is a large warehouse scale computing facility. I mentioned that it is 100% chillerless, 100% waterside economized. We were able to implement this type of a design because the favorable weather conditions in that region of Belgium, and also that we allow for an expanded thermal operating range in these facilities, which means that we're operating, certainly at the high end of the recommended range, but we also allow for a certain number of hours per year of excursion. We know that during the hottest summer months, for a few hours, there may be some temperature excursions for a brief period of time, and that's okay. We know that, we plan for it, we allow for that. And I know that to you and I, perhaps, a region that gets up to 100 centimeters of rain every year may not be considered as an ideal climate, but actually for this data center, it really is just fine. I mentioned that this was a 100% gray water use also. There's the industrial canal about 400 meters away from the site. It's the Nimy-Bleton Canal. And we built a on-site water treatment plant. So we extract water directly from the canal, and that water is actually pretty filled with hydrocarbons and things like that. So we have to purify it and clean it and filter it just to the level of industrial use. We don't treat it to make it potable water. We just treat it to make it good enough for cooling towers. And then we pump that to our water storage tanks where it's used as the water supply for the cooling towers. Okay, on to Ireland. As I said, this is a relatively smallish colo. We've leased this facility for a number of years, and we needed to do a retrofit to the ground level of this facility so that we could accommodate more engineering tasks that we had going on there. And so because of the constraints of the facility and whatnot, our team took a look at what options were available, and we decided on an airside economized solution here. This is in Dublin, Ireland. It is a 100% airside economized solution, and we do have a direct evaporative cooling module designed into the air handler. And we also designed a custom hot air capture solution here. This was put online in the second half of 2010, and this is our second chillerless design in Europe. Once again, we've heard a little bit about favorable weather conditions, but you really do have to pay attention. If you're going to maximize the solutions and maximize the options available to you, you really need to look at what you can do based on the local climate. In Dublin, for the vast majority of the year, the outside air temperature and humidity is excellent for an airside economized solution. And there were other constraints here. It was an existing building. It's in a major city center. There were space constraints, and so we didn't have the option of maybe looking at putting up a large cooling tower installation. So based on all of the conditions that we had working for us, we decided on the air economized solution. This is a schematic of the air handler. There's outside air is extracted and taken into a mixing chamber where it can either be brought directly through to the data center through the filtration units and through the direct evaporative cooling unit, or it can be mixed with return air if the outside air is too cold for direct use. I'll talk a little bit more about the direct evaporative cooling in a minute, but notice also that it goes through a common supply air plenum so that then this cold air is introduced to all the cold aisles through a common plenum, and then the hot air is captured through a custom hot air capture system and then extracted out of the data center or mixed in with the incoming air. This is a picture of the hot aisle capture system. And this picture was taken during our system testing where we are using the artificial load banks you see pictured here to serve as load to verify the functionality and efficiency of the system. I talked that we designed a direct evaporative cooling module into the air handler. The purpose of that is twofold. Really, it's used for peak temperature shaving during the very warm summer days where you can use direct evaporative cooling to cool down the outside air. And also during the very dry and cold winter months, it's used for humidification as well. Okay, now we're on to Finland. This site was a former paper mill. It was built by the Stora Enso company in the early 1950s, and it was an operational paper mill until 2008. Google acquired this site in 2009, and since that time, our team has been busy designing and constructing and testing the operations of the facility. We've done this with our design build partner, DLB, and we are currently in integrated system testing and commissioning of the first phase of this facility. The unique feature of this site is that we've deployed a 100% seawater cooled solution. There were definitely some benefits of this site, well, not the least of which is that it was built right on the shores of the Gulf of Finland, and it really lended itself for this type of a cooling solution. And there was a lot of existing infrastructure on the site that we wanted to reuse so that we wouldn't have to have such a large environmental impact on the construction of a new site. The design also allows us to use almost no potable water. The water supply is directly from the seawater. The only potable water use is in the office area for drinking water and lavatories and things like that. And we reused a lot of the existing infrastructure, the buildings themselves, as well as a seawater tunnel that was already built that I'll show you soon. The basis of this design, as I mentioned, takes in fresh seawater directly from the Gulf. We pump that seawater through cooling modules, which are direct water-to-water heat exchange modules. And then the water is gravity fed from the cooling modules back out to a tempering building. And this tempering building serves the purpose of mixing incoming seawater with the outgoing return water, so that when we return the water to the Gulf, it is at a temperature more similar to the incoming water. Therefore, we minimize any chance of environmental impact on the water return. Technically, this wasn't really required, but through some of our thermal modeling, we decided to go ahead and build this, this tempering building. This is a picture of the seawater tunnel. This was constructed during the 1950s when the site was built. It's a very large tunnel. You can actually drive a construction tractor directly through this tunnel. It runs about a quarter mile long from the intake system to the pump house, right under the original mill building there. And we were able to reuse this. It's carved out of basically solid granite. We actually sent a robotic submarine with cameras and lights down through the entire length of the tunnel to inspect it before we reused it, and found it to be in really excellent condition still. So we've been able to reuse this infrastructure here. There were definitely some design challenges that we had to accommodate for. There were thermal modeling that we had to do on the effects of the seawater temperature at different times of the year, and various different effects that I'll get into. You have to accommodate for potential of fouling of your cooling systems because of the seawater, and also potential debris that might get into the system. And so we deployed special materials to accommodate for this. As you know, seawater is corrosive. So we used fiberglass reinforced piping for the main seawater supply, and we used titanium plates in the heat exchangers. You know, seawater cooling is not unique to industry. The paper mill used it. Several other industries use direct seawater cooling already. We took and employed this in a data center environment, and so, you know, taking lessons learned from other industries and applying them for unique cooling solutions to a data center industry. The thermal modeling that we had to perform was pretty extensive. We did this to understand the effects of wind direction and force on the seawater temperature. We wanted to understand the tidal effects, the ebb and flow tidal effects at different times of the year, what it does to the water levels, and the temperature and density of the seawater at different elevations below sea level, and the different thermoclines that are in this Gulf of Finland. We used about 30 years worth of seawater temperature data that was available to us from the local agencies there. And this analysis was used to drive the decisions about where to locate the intake system and where to locate the return water system, and also how far below the surface we should position these structures. And as I mentioned earlier, the output of this analysis also helped us in the decision to build the tempering building so that we would be treating the water on the return water. You know, in the sea, there's several things with the direct seawater cooling system that you have to take into consideration. Because there's no mechanical cooling here, the heat exchangers are the heart of the system, and we have to make sure that those heat exchangers remain in good condition. We implemented 4 levels of filtration and screening, going from very coarse to very fine, so that we can maintain the integrity of the heat exchanger system. And we also designed in something, considering the operations of this facility over the long term, the ability to maintain the integrity and the efficiency of the heat exchanger. So we designed in a clean-in-place solution that allows you to isolate a heat exchanger and run a cleaning solution and water to flush it out without having to totally disassemble the heat exchanger and clean each plate individually. So this was done really for ongoing OpEx considerations and for maintenance and operating costs. Like I mentioned, we used fiber reinforced piping for all the main seawater intake system and titanium plates in the heat exchangers. Another consideration that we had to really think about was something called water hammer. And I'm sure that each of us has probably had the experience in our homes. If you shut off a faucet or a valve really quickly and you get that banging in the pipes, that's water hammer. Only in this case, it was going to be on a much, much, much larger scale. What it means is that you can get these pressure waves forming in the pipe. In the event of one of our seawater pumps shutting off suddenly, you can get a temporary vacuum forming in that pipe. And while the fiber reinforced piping is very strong in tensile strength and can withstand a lot of pressure that way, it's not as strong in compressive strength. And so if there was a vacuum to be formed inside that pipe, it could lead to a failure. And so we designed in pressure regulation devices. These are these air orifices or these air valves to regulate the pressure differential in the event of a seawater pump failure. So as I mentioned, there's a lot of special considerations you have to think about if you're going to use a seawater system. On a very small scale, because of the amount of engineering effort and the one-time kind of non-recurring costs that went into the design and modeling of the system, it may not be financially attractive on a very small scale, but there's great benefits that come along with it also. First of all is that this is a very dependable heat rejection source, especially with the Gulf of Finland that freezes over every year. So it's a really nice, cool thermal source. Very low water use. As I mentioned, all the water is returning back to the sea, and the only potable water is really for office space use. And a very low PUE that we're expecting. It's not in operation yet, so I can't tell you what the PUE actually is right now, although we're expecting it to be on par with our other European facilities. So I wanted to summarize, free cooling is very important to us. We believe in it, but there's no one right answer. And I think that, you need to really look at the opportunities that you have before you based on geography and climate. Don't be boxed into one solution, and think of how you can maximize for the long-term total cost of ownership of this system. All three of our systems are completely different designs. They are all 100% chillerless, and they all employ highly efficient and reliable cooling methods based on those local environmental conditions. Okay, there's a short video that goes along with this that takes us through the cooling system in Hamina a little bit more. One of the things that makes me really proud is when our team looks at a site and looks at the unique characteristics from its geography, existing infrastructure that's already there, the climate in that area, and then designs something specific to really make the most efficient cooling and power infrastructures possible for these data centers. So we have this new data center site in Hamina, Finland, that was originally a paper mill. It was designed and built in the early 1950s. You walk the site, and first of all, it's very impressive. It's very large, and it's really a beautiful site. It's in a gorgeous area of the country. We acquired the site in 2009, and our team was really anxious to utilize the opportunities of it being right on the Gulf to come up with an innovative and very efficient cooling system for this new data center. We take raw seawater directly from the Gulf of Finland. We run it through a seawater tunnel that was actually existing. It was already built for the paper mill back in the 50s. And we pump seawater through that tunnel, and then we run it through heat exchangers, and then we actually use direct exchange through those heat exchangers to dissipate the server load heat from the data center, and then we return that seawater to a tempering building where we take in fresh seawater, mix it with the outgoing warmer water so that when we return it back to the Gulf, we return it at a temperature that is much more similar to the inlet temperature so that we minimize any environmental impact in that area. There's no compressor-based or refrigerant-based cooling here. It's all natural seawater cooling. So I think the takeaway is don't look at what has been done as the only way it can be done. Think outside the box and look at the unique characteristics of each site. I'm really happy and proud of the way the team took on this challenge and created one of Google's most advanced and most efficient data centers in our whole fleet. Okay, thank you very much. Any questions? Paolo, right here.
Hi, I'm Mikko Pervilä from the University of Helsinki. In Finland it's pretty cold, so we're usually quite stringent about wasting any heat. Have you had any talks about reusing that waste heat for the city of Hamina, for example?
You know, we haven't. Right in that area of Hamina, I mean, the site is located. The site is located, you know, kind of on the outskirts of the city of Hamina, and so it's not near a lot of population density or anything like that. So, you know, we could potentially reuse that heat for maybe warming our own office space or something like that, but we didn't really think that it would be financially worthwhile to investigate at this point. So the short answer is no. We did not investigate, you know, reuse of that waste heat. Yes, right here.
What is the usable delta T you get from the seawater through the heat exchangers?
What is the usable what? I'm sorry.
Delta T, the temperature difference you can make use of.
So at all times, under the worst temperature conditions on the inlet side, we will still be returning the seawater at less than 30 C, and so you know, at the surface, this water temperature might be up to 22 or 23 during some warm summer times, but we're taking the water in below the first thermocline, so it's about 7.5 meters down that we take in the water. So we still get a pretty good delta T across the you know, across the heat exchangers. We don't talk about the specific numbers. No, I'm not going to release the specific numbers, but the data center is designed to operate in the cold aisle at the high end of the you know, the allowable range.
So I have a question. If you weren't reusing the energy, how is the seawater economical? You could use free air cooling in Finland. It's quite cold.
How is the seawater? I'm sorry.
How did the seawater cooling make economic sense if you could just use free air cooling instead?
Oh, as opposed to, I see. You know, because there was a lot of the existing infrastructure here and the whole seawater tunnel and the pump house and the paper mill used seawater cooling for their own process. So we really wanted to minimize the amount of new construction. And so we wanted to try and make use of all the existing infrastructure that was already there. So I don't have the exact numbers about whether it would have been more viable to just use direct air, you know, outside air cooling. Certainly it's possible, but there were other considerations with it being right on the Gulf. That outside air would be, you know, it's a little bit salty as well. And so we were obviously concerned about contaminants and corrosion effects inside the data center as well.
Thank you.
On the Irish project, now it's running. What cold aisle temperature have you got, and what hot aisle temperature have you got? What are you running at?
So, cold aisle temperature there is designed to be about 27, and hot aisle temperature is, above 35-ish.
We have one question there in the middle.
On the sites where you've been using seawater or canal water, have you run into any regulatory issues, environmental impacts? For instance, in Belgium, I know if you take water, heat it up, and put it back in the canal again, you'll pay quite some additional surplus on water usage, even if it's from canal water.
In Belgium, specifically, no. We didn't run into environmental issues because several industries along the canal use canal water already, and so there is a metering chamber that it first flows through, and we are billed based on water consumption through the canal. But we're treating it, and we're actually releasing it much cleaner than we took it in. So we're not facing any concerns that way.
And also, just to clarify, so in Belgium, we're not returning warm water to the canal, right?
No, that's right.
The water
yes.
is evaporated, and then the blowdown water from the cooling tower goes to the regular city, stormwater system. So only in Finland are we returning water to the sea. Right? In Belgium, we're just taking it instead of taking drinking water, and then it goes into cooling towers. It evaporates, and then the blowdown goes to the city water system. And the blowdown is actually quite cold, so it's not warm.
Okay. Well,
Thank you very much.
thank you.